So we did 1994 yesterday, and we had started to have a good discussion there. And so 97 is a continuation and kind of a reoccurring theme. So every year on the AP exam, they're always going to ask you concepts about Coulombic attractions, effective nuclear charge, the force of attraction, that equation that we talked about. So just get that equation in your head. So again, and you don't ever have to do a calculation with that equation. You just have to be able to discuss it. And most of the time, the variables that you'll be discussing is the distance and the force of attraction, also known as Coulombic attractions. So we had a good discussion yesterday about if something became more positive or more negative. So if something becomes more positive, what happens to the distance? Goes down, which causes the force of attraction to go up or increase, and vice versa. If we go ahead and talk about something getting more negative, then the opposite occurs where the distance increases and the force of attraction decreases. Okay. All right. So let's look at A. It says, 1997, explain each of the following observations using principles of atomic structure and or bonding. So A, potassium has a lower first ionization energy than lithium. So looking here on the periodic table, so we have our lithium and potassium on the periodic table. Okay, so it's always a good idea to have a reference to what the question's asking. And so why does potassium have a lower first ionization energy than lithium? What could we possibly talk about? Coulombic attractions. So in this case here, potassium is or has what's that? Okay, so the distance is much greater. Oh, let's use a different color here. The distance in which that electron that it's being, that distance in which that electron is being pulled off, because again, what does ionization energy deal with again? Amount of energy needed to remove an electron. Awesome. So the distance, this will be a third attempt. The distance is greater, therefore the force of attraction is lower, which does give us evidence for our lower first ionization energy. And that is all you have to say. Honest to God, it's because potassium's radius or first electron is farther away from the nucleus than lithium's, then the force of attraction is much lower. Easy points. Because potassium has such a larger radius, or the first electron is farther away than lithium's first electron, it has a lower ionization energy.
Do we have to say why it has a larger radius, like since it has more core electrons?
Very good. So in terms of the potassium having a larger radius, you could say that it's in the fourth energy level versus lithium in the second. I would definitely put that in.
Can you say it has more core electrons, or do we have to say?
No, I wouldn't talk about core electrons on here. More orbitals, more energy levels, something along those lines.
I'll do orbitals. I said all of those. Energy levels confuse me.
Okay.
Sorry, didn't you do the core electrons?
Not in this case. It is a true fact that the potassium has more core electrons, but that has no bearing on the first electron. It's all about the radius.
Mr. Craig.
Yeah.
Stupid question, but what would you put on the top of that equation? The distance, I know the bottom is like the distance, the radius. Yeah, what is that?
Nothing in this case. So the charges don't change. So in this case,
what does that stand for in general? I don't know, like what would I usually put in there? Because I understand like majority of the stuff that we're like learning right now, it's just really what you have up there right now that's confusing me a lot.
So the only time we're going to talk about the positive and negative charges is when it becomes more positive or when it becomes more negative. most of the time, I'm talking 99.9% of the time, these are your variables that you're dealing with. Okay? So in this case, we don't mention anything with the positive or negative.
So then it would just be like 1, or like what would you put up there? Because it's like an equation.
Well, in this case, the protons and neutrons are the same for both, so it has no variable. It has no factor. It's when one becomes more positive or becomes more negative as a result.
But in this case, the positive and negative, we don't.
They're equal, so it's not an issue. And again, when we talk about it being more positive, or I'm sorry, when it's more negative, then we directly start talking about the distance as well. So when you talk about the charge, you're automatically going to jump down to the distance or radius as well. And we'll do that here in a second. All right, let me look at this real quick. Larger lithium does not have a larger radius.
Oh.
Potassium has a larger
Yeah,
radius.
that's what I meant.
We'll make sure you say that.
Okay, well, okay. I was trying to write as he spoke.
Again, wherever you have lithium, put potassium. Wherever you have potassium, put lithium. All right, letter B. The ionic radius for nitrogen. Actually, let's go to the periodic table. Go away. So the ionic radius for, these are the ones we're talking about this time. So the ionic radius for nitrogen with a -3 charge is larger than that of oxygen with a -2. Okay. First of all, who has more electrons in this case?
Neither.
Very good. Neither. They're the same. In other words, they have 10 electrons because they're trying to be isoelectronic with the nearest noble gas. However, why is nitrogen bigger than oxygen?
Because it
Has less core, or not less core, just
has
it's Coulombic.
less protons in the nucleus. Therefore, it has a more negative charge, which increases the distance, and then that
Okay.
increases the force.
So we can now talk about, come on, there we go. So we can now talk about that the nitrogen is more negative because the oxygen actually has more protons. Now we don't have to do an equation with this, but we can discuss this. Since nitrogen has more of a negative charge than oxygen in terms of protons versus electrons, the distance for nitrogen is what? Greater. Therefore, the force of attraction is lower. Having this equation in front of you while you're doing an explanation is huge.
And we can put it on there.
Oh, I would write that equation every time and draw the arrows accordingly, and then have the discussion about that the nitrogen's more negative. Therefore, the distance is going to be larger. Therefore, the force of attraction is going to be smaller. Okay? What am I looking at?
We're going to look at all of them later, but for now.
It's more negative. Yeah, I like it. It's doable.
Is all we need to say is nitrogen is more negative, so the distance is greater, low in force.
Nitrogen is more negative.
Because the oxygen has more protons.
Bingo. Make sure you're including protons because
And then-
both have the same number of electrons.
Yeah.
So discuss protons and electrons.
Then you go into the more negative.
The more negative has a larger distance according to the Coulombic attraction equation. If you want to mention that, that's fine. Or just say force of attraction equation and then have that written down. As the distance gets smaller or greater, then the force of
So
attraction
we
gets
should
lower.
write according.
I would always include this.
According to.
Why did you say it was doable? What do I need to delete?
So what would you write as your answer for that? Like, how would you word that?
I think I did. The ionic radius for nitrogen is larger than oxygen. That was given. The reason is nitrogen has fewer protons than oxygen. So you're dealing with the positive charge. Nitrogen's distance is greater because it has a lower force of attraction.
Okay.
All right, letter C. A calcium, actually, let me pull this up. Come on. Calcium and zinc are our conversations here. Okay. So we have calcium and zinc. All right. So the question says, a calcium atom is larger than a zinc atom. A calcium atom is larger than a zinc atom. What should we definitely talk about here? Say it again. Okay. Not saying it's wrong, but let me draw an image here. Core electrons should definitely be in the conversation. So calcium and zinc have the same number of core electrons. True or false? True. Okay. So since they have the same number of core electrons, calcium is going to be larger because, now let's talk about the equation. Why? Or zinc is smaller. Which one do you want to talk about? Zinc being smaller or calcium being larger? I like zinc being smaller. So now we can focus on what aspect of the nucleus. Oh my goodness. The nuclear charge. So we have more of a positive charge in zinc than we do calcium, yet the core electrons are the same. Therefore, the distance is going to be smaller and the force of attraction is greater. Therefore, the remaining electrons are going to be drawn in more tightly. Okay. So zinc is smaller because, zinc and calcium, same number of core electrons. Zinc, more protons. And if you want to do bullet points, there is nothing wrong with doing bullet points. You don't have to write complete sentences. So like if that thought comes into your head, zinc is smaller because, or actually just start off, same number of core electrons. Zinc has a smaller radius because there are more protons in zinc than there are calcium. Another bullet point, the radius is smaller, therefore the force of attraction is greater. Last bullet point, that's why the electrons are drawn in more tightly. A lot of stuff there. I will share this video with everybody tonight.
Thank you.
So zinc has more protons.
Zinc has more protons than calcium. Oh yeah. Yes. Yep,
So
that's huge.
has a more positive nuclear charge.
Has more of a positive nuclear charge. Or if you want to just look at the equation, the positive charge is greater than that of the calcium, while the core electrons are the same. Now, we can talk all day about valence electrons and the electrons in the d orbitals, but the more protons you have within the same row or period along that periodic table, then it's going to draw those in more tightly. That's what helps explain the trend as you move left to right along the periodic table, that generally speaking, the radius gets smaller. There are a few hiccups, but as you have the same number of core electrons up here, okay, that's the negative influence that's blocking, quote unquote, the positive charge within the nucleus. Okay. Isn't this fun? Don't you guys love concepts?
No. Last
I
unit
know
was
you're
the
lying
only
to me.
good
Just
concept unit.
who is?
Last unit.
No.
Yes, because that concept
I
makes
was
sense.
that.
Well, the equation, you had to just memorize what each thing did.
Oh, that's true.
Yeah.
That wasn't really.
Yeah.
It was exactly. It's considered
nice
a concept. Thank you.
because it was mostly math with a tiny bit of concept sprinkled in. But this one's all concept.
All right, we're ready for the dumbest question of the batch. Boron, the moron, has a lower first ionization energy than beryllium. Boron, so we're looking here and here. Now, I can't remember if it was this period or sixth period that we had a pretty good conversation about orbitals within an energy level. Was it in here?
I doubt it. We don't have good.
I remember.
Go ahead. What did we say?
You remember this?
Yeah, I don't
If you
remember
pull
this.
from a higher orbital greater like 3s, you're going to need less energy than 20.
Okay, we did talk about that. Did we talk about the orbitals in the same energy level?
Yes, about how you added, like, you talk about when we added, you have to fill up each orbital and then go back and do the other.
Mm-hmm. Yeah, yeah.
We talk about that, but
So it's easier to pull from an unfilled orbital than this, like that's like, so like a 3s orbital that's filled is harder to pull from than a 3d orbital that's not.
I like that. So let me draw a picture here. So we're in the second row. So as we fill up, go ahead and do this. 1s, boom, boom. So the 1s is full. 2s, we just filled up, but we're still in the same energy level. And there's 1, 2, 3. So I'm going to go ahead and separate the first. Oop, that didn't work out too well. Separate the first from the second energy level. Okay. So to kind of get a picture of what's going on here, make it a little thinner.
Oh, I think I get energy levels. That's kind of cool.
So if I look at, say, that's bad. So the nucleus, way too big, way too large to scale. So we have our first energy level, second energy level. These are representing s orbitals. And then the p orbitals, God, these are bad. They look like propellers, but there should be like 3 of those that are propeller type things. Really bad, really bad. I apologize. Not an artist. So as we fill up the 1s orbital, and then we fill up the 2s orbital, so that's beryllium's electron picture at the moment, this terrible drawing.
Yeah.
And then I put 1 electron in here. Okay. So as we start to fill the 2p orbital, the boron, which is represented with the 2p orbital electron occupying it, is easier to remove. What also should be said, as you continue along, oops, sorry, I was on the periodic table. As you continue along, going from boron to carbon to nitrogen, what happens when you go from nitrogen to oxygen? The energy goes down again. And the reason is because going from boron, carbon to nitrogen, we just put 1 electron in each of the orbitals. And with oxygen, now we're starting to double up. Okay. So I like the conversation, must have been a 6th period that we had this. As you fill up an orbital, okay, as you're filling up orbitals, what are you also placing within the nucleus? As you fill up orbitals, and we'll pretend that they're neutral, as you fill up orbitals, what else are you placing within the nucleus? Protons. Good. So as you start to drop more and more protons as you move along, as I erase things instead of write, as you drop more and more electrons, we're now starting to build up the nuclear charge. So that also does cause the s orbitals that are already filled to get smaller. So they actually start to compact within even more. And as we start to drop 1 electron into each of the p orbitals, then they start to get smaller and closer to the nucleus as well. So if you're thinking about having an s orbital and a p orbital, the p orbital with 1 electron isn't as close as it could be as if it had a half filled or completely filled. Now, that's kind of a garbage explanation, but that's what College Board's looking for. So using the equation of this here kind of works. Okay. You could say the reason is that it has a higher ionization energy is because the distance is greater. Now, I don't see too often where College Board's going to argue with you on that because there's only 1 electron. I'd probably talk about there only being 1 electron in the p orbitals where it wants to have 6 or would like to have 3, but it's just not as close. And also when you fill up an orbital, like the 2s orbital that got filled up, it's a lot harder to remove that electron. So there's a lot there. And that's why I'm not a big fan, but I have seen this question asked more than I'd like to, which also happens to be the last one that they did yesterday. So they're dumb questions. I would say the reason is because you just filled up an s orbital. You're now dropping one electron into the p orbital. The charge or the effective of the Coulombic attraction isn't as great for that first p orbital electron than it is with the 2s. It really, it goes against the pattern, the trend, but it's an anomaly that happens. And I'm surprised that they ask.
Let's just hope they don't ask it.
Oh, they will. Don't worry.
Will that be on our
Yeah, probably.
the test?
Sure.
Why? If you don't like it, then don't put it.
Because just because I don't like it doesn't mean it won't show up in May. All right, let's do 99. Get your calculators out, boys and girls.
You see, the reason I did good on the last is because it's all math and equations that were given to me.
I feel like I didn't write that right, but I also didn't prove it, so I just kind of put some stuff down.
You ought to be a bullet point woman. Seriously.
Yeah.
Because these are thoughts, but they're not incorrect. So it's okay to talk like Tarzan
Okay.
with bullet points. You don't have
Well,
to
then I
write
can talk
complete.
like Tarzan and Susan.
Yeah, but it's easier to look and go check, 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 check.
Okay.
It'll work.
Okay.
All right, 1999. Answer the following questions regarding light and its interactions with molecules, atoms, and ions. Ooh, yeah. Now, there were more parts because it has A, so there was a B and so on.
You calculated for me?
Oh, my God. Where's your calculator?
At home.
Good place for it.
Yeah.
Oh, because you were working hard with it on
Sorry,
e-learning?
for the past 4 days.
Uh-huh. All right. A, the longest wavelength of light with enough energy to break a chlorine single bond is 495 nanometers. I, calculate the frequency. You shouldn't have the frequency equation on top of your head. You need that other equation sheet.
I know. That's why I was asking people because I didn't want to get my. Neither of you have yours out.
You have the periodic table out for us, the Vesper sheet.
I got nothing.
I got it right. Oh my gosh, it's the first time I've ever done that. Okay.
Thanks, Greg.
All right, let's see.
Bro.
Did we do this unit? I don't
Yeah.
even remember.
Well,
A while ago.
Frequency.
we did it
Is the
not too long ago.
So it gives us wavelength and mean frequency. I know which equation to use.
Uh-oh. It's Joule second. So the equations you see up there, those are the only two we care about. You're also given two constants, speed of light and Planck's constant, which are on your equation sheet. Top right, top left corner of one of the equation sheets. So if you're looking for frequency, what must we do to nanometers?
Make it
Got to be in meters because speed of light is in meters.
per second. Speed of light.
Well, yeah.
So
What's that? Nano 9. I love it.
I actually
Not negative 9. 9. 4.95 times 10 to the negative 7 meters. Okay, so it wants the frequency. So we'll use this equation. So we have a length. That's what dinosaur represents. So that's length, that's frequency, that's a constant. So I would advise rewrite. Yes, you will have math on the test.
that's good.
Good. Nothing else.
I think on your equation sheet it says 2.998 if you're using 3, I'm good. I can live with it.
I cannot.
Get on fire.
1 over seconds.
I made a new day.
Booyah.
And in this unit, it matters what you do.
You better believe it. So meters cancel and 1 over seconds.
Yeah, there's no money we don't have to. No. Those didn't count. Get on.
What are we getting on?
Good.
Are you playing games,
I'm
Eli?
not doing anything.
I'm aware you are doing nothing. I think it's 606 repeating.
But you did it,
Yeah.
remember, Joe?
What's that?
You used the wrong number.
Oh, you
I used the wrong number.
Yeah.
Oh.
used 3, they used 2.98.
Okay,
I got that too, because I used 3, but.
nice.
Alice, you used the wrong number.
Double I. Calculate the energy. How in the world could you ever do that? Oh, we just calculated the. God, rough.
Mr. Plink.
And what we just had.
.6 do 6 seconds EE negative 34. Alice, did you get 4.013
Yes, I did.
times 10 to the negative 19
Yes, I did.
And that would be, whoop, that's an ugly jewel.
in joules because the seconds cancel out with the per seconds.
Baby.
Let's go.
Okay.
I like these questions.
Of course you do. That's math. Here we go. Calculate the minimum energy in kilojoules per mole of the chlorine-chlorine bond. So we're actually doing a little thermo now. It's okay because we did that before.
We did?
How in the world could we possibly figure out the minimum energy in, here, let me highlight it, kilojoules per mole? Hayden Schmidt, what would you do if you were asked this question in the future? False.
Oh,
What was the first thing you would do?
Change it. Oh,
Attaboy, now we're cooking.
You did have that confidence, though.
Kinda.
How hard are these questions on scale 1?
These are impossible. Just look at
I
Eric.
agree.
He's struggling.
I was kidding when I said.
Oh, Eric, you can't kid
Eric, I
me.
ain't doing them.
I know.
Oh, wait. No.
Oh, wait.
Just kidding. Don't know.
Oh, please don't.
Okay.
I thought I knew.
So how in the world could we ever find out how many moles per mole?
Dude.
Didn't we talk about this? And
I think
we
so.
had to do like but we had to do electrons then. This is
Okay.
electrons.
Electrons are fine too.
Oh, is this when we were e-learning?
I think so when we were e-learning.
Yeah, because you asked me a question I didn't know the answer.
You asked everyone and no one knew the answer.
And then you were, because oh, we use avocados. No, I'm sorry.
We would use avocado.
That's right. Because we can go from kilojoules to,
Well, we want to be in kilojoules per mole.
so we have to use, I don't remember actually, but I know we used avocado's number. because
Did
went
we
from-
not do, this is the amount of energy for one chlorine bond?
No, we did it when electron was.
No. I'm talking about this question.
Um,
Did we not just find the amount of energy for one
Oh.
chlorine bond?
so why can't we just divide it by avocado's number?
You mean find out how many moles that would be of chlorine bonds?
We wanted it per mole.
What, dude?
Oh, but then we can divide.
Booyah! There we go.
I knew.
No.
Just kidding. I don't know why. I did not really know it.
So chlorine bonds. So remember, Avogadro's number is just a number until you put a unit on it. So our unit in this case is chlorine bonds.
That's a made up unit.
It is not a made up unit. So whatever the inverse of Avogadro's number,
That's
What was he measuring when he found
6.66.
Avogadro's number?
Oh my goodness.
pies. I don't
That's a
know.
bad number.
It's a good number.
No.
You just throw out Avogadro's number in for bonds.
All right.
I don't know. Chlorine. Actually, we're just going to leave it as moles by Gumby.
Wait, how do you do that?
How'd I get what?
1.6.
They didn't give me no teaching degree.
Wait,
That's
Craig, you lost us.
Where did the 1.66 times 10 to the negative 24?
Oh,
I think it's when I took the inverse of Avogadro's number.
because you did one.
The
over.
inverse?
Yeah,
What?
1 divided by Avogadro's number, so I can get mole. Remember, Avogadro's number
Okay, got it.
is that many things per mole. Well, I need to get rid of that many things and flip mole so it's on top.
Just Craig, can you just like to be safe?
Uh-oh. To be safe. Uh-oh. Oh, God. Here we go.
Because that's just looking at it, seeing 1.06.
241.6 is my final answer.
241.8 in my book.
7 in mine. What in the?
Well, you have 749. You have 749.
Yeah.
Okay. So round the 9 to 5, round the 5.
Isn't that what you're not supposed to do?
What do you mean you're not supposed to?
Like you're not supposed to take you're not supposed to round the 4.
Do you have
to
an
5,
ability
and then
to
the
find
5
out how many like fixed numbers? The answer is yes.
What?
Significant figures.
No, not sig figs. It's where you're truncating where I'm rounding.
I'm confused.
All right. So I want to make sure everybody is clear on what I just did there.
No.
No, I'm not.
Yes.
What in the?
Hang on. Jacob speaking. Okay. So remember that Avogadro's number represents, in this case, that many chlorine bonds per mole. So we started with 1 chlorine bond. So I need to get chlorine bond down here with mole on the opposite side. So I'm letting the algebra cancel out the chlorine bonds where I'm left with moles. So I had to flip the mole and Avogadro's number and the unit mole in that case, so that the chlorine would cancel out. Isn't that fun? It's called dimensional analysis. 241, actually 242 if you were doing sig figs.
Okay.
Actually, with sig figs, it would be 242. Because it's per mole, and you were given, it was to break a single chlorine bond.
I think that's good. That's
Now,
pretty
the
good.
key is, this is asking for, I have a mole of them, how much energy is needed. So this was a lot similar to the first question, I think in topic 4. I can't remember.
I think
All
that's
right.
pretty good for today.
Let's see. Hang on here.
What the schedule said.
Ooh, I don't want
Yeah, we're going to call it a day. This will be a good one to start with tomorrow.